In this video, we're going to be looking at how to write the form of a line in 3-space. Now, in 2 dimensions, we just have a single linear equation to create a line. But in 3 dimensions, we either have to represent the line as an intersection of planes, or we have to represent it in parametric form. So there's 2 main ways that we're going to represent a line in 3 dimensions. So we're not usually going to actually represent it as the intersection of planes, although fundamentally that is where all of these come from. We can represent it in parametric or vector valued function form. These are really basically the same thing except for the notation. And then the second way that we're going to represent this is in symmetric form. Now, symmetric form, again, it can be derived from the parametric form, or it can represent the actual intersection of planes. There are going to be certain kinds of circumstances where it will look much more like the intersection of planes. But we're going to address the sort of general case first, and then we're going to look at a special case where the symmetric form becomes somewhat problematic. So in both cases, the direction of the line is represented by a vector, which sometimes is referred to as u. And so we're just going to call that here. Vector, we'll call it ABC as the components for now. And then also that direction is one thing, but we also have to get it to pass through a point in space. Otherwise, there's an infinite number of lines that go in this particular direction. So the point in space, again, formulaically, would be represented as x naught, y naught, z naught. Now, let's start with the parametric or vector valued form. So in the parametric form, we would have 3 equations that collectively work together. In the vector value function form, we collect those into a single vector valued function. So we would have x as an equation, any x is equal to a t plus x naught. Y is equal to bt plus y naught. And z is equal to ct plus z naught. And in vector valued function form, this is equivalent to a vector where the first component is at plus x naught, and the second component is bt plus y naught, and the third component is ct plus z naught. So let's look at a particular example. Suppose I want to create the equation of a line pointing in the direction of 3, -2, 4, and passing through the point -1, 0, 7. So then my parametric equations would be 3t minus 1, y is equal to -2t plus 0, and z would be equal to 4t plus 7. And so in vector valued function form, (3t minus 1, comma, -2t, comma, 4t minus 7. Now, in symmetric form, basically this is derived from solving each of our equations for t, and then setting all the t's equal to each other. So this would end up looking like x minus x naught over A equals y minus y naught over B is equal to z minus z naught all over C. So in this particular example, we would end up with x plus 1 all over 3, and then y all over -2, because it's y minus 0. And then the z would be z minus 7 all over 4. Now, what this actually represents are planes. X plus 1 over 3 equals y over -2. That is a plane. And you can solve it for x and y, the constant, that's a plane in 3 dimensions. Similarly, y over -2 equals z minus 7 over 4. This is also an equation of a plane. And somewhat redundantly, if I took x plus 1 over 3 and set it equal to z minus 7 over 4, that would also be a plane, but they all intersect on the same line. So I really only need 2 of the planes to obtain the representation of the line. So that's really what's going on here. But this is a compact way of writing this. And again, you can also derive this formula by taking your parametric forms, solving for t, and then setting t equal to everything. Now, this form of the symmetric equation in particular becomes a problem if one of the slopes is 0. Well, if the direction vector contains a 0, nothing changes about the equations in parametric form. You would just have a 0 as one of your coefficients for t, and so your equation for at least one of the variables would just be a constant. When you have a symmetric form, though, you can't divide by 0, so you actually end up not being able to use it. What you end up having to do is some combination of the symmetric form, which two of them will represent a plane, and then comma a second equation, which is that constant expression. So consider 2, 0, 5 as my direction vector and my point 1, 1, 1. So in, let's say, the vector valued function form, I would get 2t plus 1, and then 0t plus 1, and then 5t plus 1, and that would be my vector valued function form. And the fact that y is equal to 1 in the middle here does not affect either the parametric form or the vector valued function form at all. But in symmetric form, I cannot divide by 0. So don't do this. X minus 1 over 2 equals y minus 1 over 0 equals z minus 1 over 5. Okay, so this is not allowed. And it will be marked wrong. So again, just so that it's clear, we're going to make this bright red. No, that's not okay. So what you would do is the parts where you're not dividing by 0, this will actually become a plane. And then the second plane would be y equals 1. Because that, again, that's the middle component of your parametric form. And the other two pieces are just representing the plane. This is the intersection of two planes. It's just that one of them is a constant. There is no change in y as you go, as there's no t in this expression to solve for. So you just end up with this. So this is important. Usually when I have a 0 in the direction vector, I will simply resort to vector valued function form because then I don't have to change anything. But if you are asked to do symmetric form or you prefer symmetric form, this is a scenario you do have to watch out for. And so you will either have to change your representation or you will have to switch to the vector valued or parametric function form to get around it.